The morning of July 2008, 1944, dawns over Ceram Island in the Dutch East Indies. Colonel Charles MacDonald leads his P-38 Lightning formation through hostile skies, their fuel gauges already dropping toward the danger zone. Flying beside him is a 42-year-old civilian named Charles Lindbergh, technically listed as an observer, though everyone knows he's been flying combat missions for weeks. At precisely 0947 hours, MacDonald's radio crackles. 7 Japanese fighters diving from the clouds. A lone K-51 Sonya bomber tries to break away at sea level, where the Zero escort should have every advantage. In these conditions, standard doctrine says American fighters can't compete with Japanese agility and should avoid the fight. But something is different today, something that shouldn't even be possible. Lindbergh banks hard, throttles forward, and accelerates. At sea level, where the P-38 traditionally struggled for range and speed, his Lightning responds like it's been transformed. The Sonya pilot glances back, eyes widening. The American fighter shouldn't be this fast. Not here, not with the fuel it must have already burned just reaching this combat zone. The head-on pass lasts 3 seconds. Lindbergh's .50 caliber rounds find their mark. Captain Saburo Shimada's aircraft disintegrates into the jungle canopy below. What the Japanese pilot didn't know, what Allison's own engineers swore was impossible, was that Lindbergh had been operating his engines in a way that violated every technical manual in the 5th Air Force, a technique that officially didn't exist, a modification so controversial that when he first proposed it 5 weeks earlier, mechanics threatened to ground any pilot who tried it. Yet here's the impossible part. Lindbergh still has enough fuel to make it home, more than enough. His fuel consumption numbers don't just break the rules, they shatter them. While standard P-38 operations at these distances left pilots ditching in the ocean or praying there, vapors held out. Lindbergh lands with reserves that shouldn't exist. The technique that made this possible? Reducing RPM to 1,600, increasing manifold pressure to 30 inches of mercury, and running auto-lean mixture. Settings that every expert said would destroy his engines within hours. This is the story of how one civilian with no engineering degree rewrote the physics of aerial warfare, extended the P-38's combat radius by 180 miles, and changed the outcome of the Pacific campaign, all while being told what he was doing was impossible. By June 1944, the Pacific War has reached a critical juncture. American forces are pushing toward the Philippines, but there's a problem that's killing pilots and losing battles: range. The Lockheed P-38 Lightning, America's twin-engine fighter in the Pacific, suffers from a crippling limitation. Its Allison V-1710 engines, rated at 1,475 horsepower each, are magnificent pieces of engineering, but they're also fuel-hungry monsters. At standard operating procedures, 2,200 to 2,400 revolutions per minute with auto-rich mixture settings, the P-38's combat radius tops out at approximately 570 miles. The mathematics are brutal, from bases in New Guinea to targets in the Philippines, 800 miles one way. The mission is impossible. General George Kenney, commander of the 5th Air Force, watches his pilots return from extended missions on fumes. Some don't return at all. The Pacific Ocean claims 17 P-38s in May 1944 alone, not from combat, but from empty fuel tanks. Pilots ditch within sight of their carriers, their fighters transformed into expensive sinkholes because they couldn't stretch their fuel just 50 more miles. The Allison engineers have tried everything. They've calculated optimal cruise speeds, they've refined mixture ratios, they've published detailed technical manuals specifying exactly how to operate their engines for maximum efficiency. Their recommendation: maintain high RPM with auto-rich mixture settings to ensure adequate cylinder cooling and prevent detonation. These aren't suggestions, they're requirements backed by thousands of hours of testing. Lieutenant Colonel Charles MacDonald, the 29-year-old commander of the 475th Fighter Group, Satan's Angels, knows the numbers by heart. His unit has the highest kill ratio in the theater, 12 Japanese aircraft destroyed for every P-38 lost. But they're handicapped by geography. Every mission is a calculated gamble with fuel reserves. The situation reaches crisis level on June 15, 1944. A reconnaissance flight over Ceram spots a major Japanese staging area. The target is strategically vital. It's also 650 miles from the nearest American base. MacDonald calculates the numbers 3 times, hoping he's wrong. He isn't. His P-38 seconds can reach the target with drop tanks, but the return trip will require ditching half his squadron in the ocean. He cancels the mission. The enemy base survives to launch attacks that kill 43 American sailors over the next 2 weeks. MacDonald watches the casualty reports pile up, knowing his fighters could have prevented this. The technical limitations aren't theoretical anymore, they're body counts. Meanwhile, Allison's engineers remain confident in their specifications. They've tested every possible configuration. They've mapped the performance envelope. The V-1710 is operating at its maximum sustainable efficiency. Any attempt to reduce RPM below 2,000 while maintaining high manifold pressure, what engineers call oversquare operation, will cause excessive cylinder stress, inadequate cooling, and catastrophic engine failure. The manuals are explicit. Do not operate below 2,000 revolutions per minute at manifold pressures exceeding 26 inches except during landing approach. This isn't a suggestion. This is metallurgical reality. The Allison V-1710 has physical limits, and those limits are non-negotiable. Violate these specifications, and you don't just risk an engine, you risk the pilot's life. By mid-June, the consensus is unanimous: the Air Transport Command has explored every option. Lockheed's engineers have reviewed the airframe limitations. Allison's technical representatives have checked their calculations. The P-38's range cannot be significantly extended without compromising engine reliability. The 475th Fighter Group, America's elite Lightning unit, with 552 confirmed victories, is operating at the absolute limits of what's physically possible. And then Charles Lindbergh walks into their operations tent on June 26, 1944, and tells them everything they know is wrong. Charles Augustus Lindbergh isn't supposed to be here. At 42 years old, he's technically a civilian consultant for United Aircraft Corporation, sent to observe operations and provide feedback on the Vought F-4U Corsair. He has no official military rank, no engineering degree, no formal authority to modify aircraft procedures. What he does have is an obsession with fuel efficiency that dates back to 1927. 17 years earlier, Lindbergh crossed the Atlantic in the spirit of St. Louis, a flight that should have been impossible. The key wasn't just courage, it was mathematics. While other aviators focused on speed and power, Lindbergh spent months calculating optimal engine settings for his Wright Whirlwind engine. He discovered that conventional wisdom was wrong. Reducing RPM while maintaining manifold pressure, despite what engineers claimed, actually improved efficiency without destroying the engine. He flew 3,600 miles on 450 gallons, landing in Paris with fuel to spare. Now, sitting in the operations tent at Mockmerdrome on Biak Island, Lindbergh listens to MacDonald explain the fuel crisis. The young colonel spreads navigation charts across the table, marking targets that might as well be on the moon. "We can't reach them," MacDonald says flatly. "The numbers don't work. Lindbergh studies the charts, studies the fuel consumption rates, studies the Allison engine specifications. What if the numbers are wrong, he asks. MacDonald blinks. Sir, your engines. You're operating them at high RPM with rich mixture. That's what Allison recommends for combat, but you're not in combat for most of these flights. You're cruising. What if there's a more efficient cruise setting? MacDonald explains patiently that Allison has already calculated optimal cruise efficiency. The specifications are based on extensive testing. Going below 2,000 revolutions per minute causes inadequate cooling. The engines will seize. Lindbergh asks to see one of the P-38 seconds. What happens over the next hour becomes legendary. Lindbergh doesn't just examine the lightning, he interrogates it. He crawls into the cockpit, studies the engine gauges, traces fuel lines with his fingers. He asks about mixture controls, propeller governors, cylinder head temperatures. He wants to know everything about how the Allison V-1710 actually operates in flight, not how the manuals say it should operate. The mechanics watch this middle-aged civilian poking around their aircraft and exchange glances. Who is this guy? I flew the Atlantic at 1,650 revolution per minute, Lindbergh says finally. Similar engine principles. The key is manifold pressure and lean mixture. You're running rich because Allison is afraid of detonation, but if you manage the mixture correctly, you can run lean without cooking the cylinders. MacDonald shakes his head. Mr. Lindbergh, with respect, the Wright Whirlwind and the Allison V-1710 are completely different engines. What worked in 1927 won't necessarily— Let me prove it, Lindbergh interrupts. One test flight. I'll demonstrate the technique. If the engines show any sign of distress, I'll abort immediately. MacDonald considers this. He thinks about the missions he can't fly, the targets he can't reach, the sailors dying because his fighters lack 50 more miles of range. One flight, MacDonald agrees. But if those engines start running hot, you're coming straight back. Lindbergh smiles. Deal. What MacDonald doesn't know is that Lindbergh has already been testing his theory on previous flights, and the results are extraordinary. June 30th, 1944, Lindbergh climbs into P-38J Lightning serial number 44-20, 3314, one of MacDonald's own aircraft. The pre-flight checklist is standard: control surfaces, fuel load, weapons systems. What comes next is anything but. Lindbergh starts the engines and lets them warm to operating temperature. Then, as he taxis toward the runway, he does something that makes the crew chief's eyes widen. He adjusts the propeller controls to 1,600 revolution per minute. According to every technical manual, every training protocol, every piece of official guidance, this is where things should start going wrong. The Allison V-1710 has minimum continuous RPM limits for a reason. Below 2,000 revolutions per minute, the propeller-to-crankshaft gearing doesn't provide adequate airflow across the cylinders. Cooling suffers. Hot spots develop. Detonation risk increases. But Lindbergh doesn't stop there. He advances the throttles, increasing manifold pressure to 30 inches of mercury. This is the over-square condition that Allison explicitly prohibits. Higher manifold pressure than RPM in hundreds. It's called over-square because the ratio is inverted from normal operations, creating cylinder pressures that theoretically exceed safe limits. Then he leans the mixture until it's running auto-lean instead of auto-rich. On paper, he's just created the perfect conditions for catastrophic engine failure. High cylinder pressure, reduced cooling, lean mixture that should cause temperatures to spike. Allison's engineers would be horrified. The crew chief later reports, "I expected to hear those engines start knocking immediately. Everyone on the flight line was holding their breath." Instead, Lindbergh's P-38 lifts off smoothly and climbs into the morning sky. For the next 4 hours, Lindbergh flies a systematic test pattern. He monitors cylinder head temperatures obsessively. He watches oil pressure, fuel flow, manifold pressure. He makes notes on a knee board, documenting every parameter. The engines run smoothly, temperatures remain within normal limits, fuel consumption drops dramatically. When he lands, his fuel gauges tell an impossible story. At standard cruise settings, this flight profile should have consumed approximately 235 gallons per hour total. Lindbergh's actual consumption, 175 gallons per hour, a 25% reduction in fuel burn. MacDonald examines the flight logs, certain there must be an error. There isn't. He has the mechanics inspect the engines for signs of stress. They find none. The plugs are clean. The cylinders show no hot spots. The oil is pristine. That is illegal, the maintenance officer says flatly, jabbing a finger at Allison's technical manual lying open on the workbench. Page 47, paragraph 3. Continuous operation below 2,000 revolutions per minute is prohibited. It says prohibited, not recommended against. Prohibited. Did the engines fail? Lindbergh asks mildly. That's not the point. The point is... The point, MacDonald interrupts, is that we just gained 180 miles of combat radius. Do you understand what that means? The room goes quiet. MacDonald does the math aloud. With this technique, we can reach targets 750 miles out. That puts the Celebes within range. Halmahera. Half the damn Philippines. Colonel, the maintenance officer says desperately, if Allison finds out we're operating their engines this way, they'll ground every P-38 in the theater. This goes against everything. Then Allison doesn't find out, MacDonald says. Not yet. Not until we've proven it works in combat. What they don't realize is that the hardest fight isn't against the Japanese. It's against their own headquarters. July 2nd, 1944. Word of Lindbergh's illegal engine technique reaches 5th Air Force headquarters. The response is immediate and volcanic. Colonel Earl Barnes, Chief of Maintenance for the 5th Air Force, arrives at Mokmar with a delegation of engineering officers and Allison's chief field representative, a man named Robert Patterson. They carry briefcases full of technical specifications, test data, and metallurgical analyses. They are not here to be impressed. The meeting convenes in the operations briefing room. MacDonald presents his case: 4 successful test flights, dramatic fuel savings, no engine stress indicators, revolutionary range improvement. He spreads flight logs across the table showing Lindbergh's consistent 25% fuel consumption reduction. Patterson listens with increasing horror. Gentlemen, he says when MacDonald finishes, what you're describing violates fundamental principles of engine operation. The Allison V-1710 is designed to operate within specific parameters. Those parameters exist because physics exists. Lindbergh, sitting quietly in the corner, speaks up. Mr. Patterson, I've read your technical manuals. They're excellent documents, but they're based on assumptions about how pilots operate engines in combat conditions, high power, rich mixture, maximum performance. We're not talking about combat operations, we're talking about cruise efficiency. The engine doesn't know the difference, Patterson snaps. Low RPM with high manifold pressure creates excessive cylinder pressure regardless of the tactical situation. You're risking detonation, piston failure, and, except we're not experiencing any of those things, MacDonald interrupts. We've now flown 16 missions using Mr. Lindbergh's technique. 16. We're monitoring temperatures constantly. The engines are running cooler than standard operations, not hotter. That's impossible. That's measurable, Lindbergh says quietly. He pulls out a graph showing cylinder head temperature comparisons. The lean mixture actually improves thermal efficiency. Less excess fuel means less evaporative cooling load. The cylinders run at optimal temperature, not maximum temperature. The room erupts. Barnes argues that Lindbergh is cherry-picking data. Patterson insists that catastrophic failure is inevitable, just a matter of time. Another engineering officer points out that Allison's testing program involved thousands of hours of dyno runs establishing safe operating limits. Are they supposed to throw all that out because a civilian ran a few test flights? Gentlemen, General Ennis Whitehead's voice cuts through the argument like a blade. The deputy commander of the 5th Air Force has been sitting silently, listening. Let me ask you a simple question. If we adopt this technique fleet-wide, what's the worst-case scenario? Patterson answers immediately. Widespread engine failures, sir, potentially catastrophic. And if we don't adopt it, silence. Because I'm looking at casualty reports, Whitehead continues, pulling a folder from his briefcase. In the last 6 weeks, we've lost 23 pilots to fuel exhaustion, not combat. Fuel. They ran the numbers, flew the mission, and didn't make it home. That's 23 pilots who followed your operating procedures, Mr. Patterson, and died because they couldn't reach targets within the P-38's approved range limitations. Patterson shifts uncomfortably. Mr. Lindbergh, Whitehead says, you're telling me you can extend combat radius by 180 miles without damaging engines? I'm telling you I already have, sir, 16 times. And if you're wrong, if these engines start failing, then pilots will notice temperature anomalies during cruise and can immediately revert to standard procedures. The technique fails safely. You simply go back to high RPM and rich mixture. But sir, I'm not wrong. The physics is sound. Whitehead turns to MacDonald. Colonel, honest assessment. Do you trust this technique? MacDonald doesn't hesitate. Sir, I've flown it myself 3 times. My entire group has transitioned to these settings. We're reaching targets we couldn't touch before, and we're doing it with fuel reserves instead of prayers. Yes, sir, I trust it. The room holds its breath. Mr. Patterson, Whitehead says. Finally, I appreciate Allison's concerns, but we're fighting a war, not publishing technical journals. Colonel MacDonald's group will continue using Mr. Lindbergh's technique, if, and only if, we see evidence of engine stress, we'll reassess. Until then, I want these procedures documented and distributed to every P-38 squadron in the theater. Patterson stands. Sir, I must protest in the strongest. Your protest is noted and overruled, dismissed. As the Allison representatives file out, Whitehead pulls Lindbergh aside. You better be right about this. Lindbergh nods. I am, sir, but there's only one way to prove it to everyone. What's that? Combat. If you're enjoying this story of innovation against impossible odds, make sure to subscribe and hit the notification bell. We're just getting to the part where Lindbergh's forbidden technique faces its ultimate test against the Japanese. You won't want to miss what happens next. July 28, 1944. The mission briefing is straightforward, armed reconnaissance over Seram Island, 640 miles from Mockmerdrome. In the old days, 3 weeks ago, this would have been impossible. Today, it's routine. 20 P-38 Lightnings from the 475th Fighter Group thunder down the runway in pairs, Lindbergh flying as wingman to Colonel MacDonald. Every pilot is using the Lindbergh technique now, 1,600 revolution per minute, 30 inches manifold pressure, auto lean mixture. The unofficial motto has become fly like Lindy, come home with gas. The formation cruises at 170 miles per hour, slower than standard doctrine recommends, but dramatically more efficient. Fuel gauges tick down at rates that would have been impossible a month ago. At the 2-hour mark, When previous missions would have pilots nervously calculating reserves, the P-38s have fuel to spare. At 0947 hours, over the dense jungle northwest of Amahai, MacDonald spots them, 7 Japanese aircraft. A lone Ki-51 Sonya bomber with 6 A-6M0 fighters providing escort. The enemy formation is at 8,000 feet. Diving toward the coast, the American fighters are at 12,000 feet, perfectly positioned for a bounce. MacDonald keys his radio, Satan lead to all flights. Tally-ho. 7 bandits, Angels 8, heading 270. The P-38 seconds roll inverted and dive. The Japanese pilots react immediately, but something is wrong. The American fighters are supposed to be low on fuel by now. They shouldn't have the energy reserves for aggressive pursuit. Intelligence briefings have been clear. P-38 seconds operating at these distances are vulnerable, forced to conserve fuel for the return journey. Easy targets. But MacDonald's Lightning screams down at over 400 miles per hour. Energy to burn, literally. His targeting pipper finds a 0, holds steady, 3-second burst. The 0's wing separates, the aircraft tumbling into a violent spin. Splash 1, MacDonald calls calmly. The Sonya pilot, Captain Saburo Shimada, brakes hard left, trying to reach sea level where the heavy American fighters can't follow effectively. The Mitsubishi A-6M0 has always dominated at low altitude. The lightweight design, the incredible maneuverability, the Nakajima Sakai engine optimized for low-altitude performance. All of these favor the Japanese in a sea-level dogfight. Shimada has survived 47 combat missions, using exactly this tactic: get low, get slow, force the Americans into a turning fight, where the 0's agility becomes decisive. He dives hard, G-forces crushing him into his seat. The jungle canopy rushes up. He levels out at 500 feet, the air thick and turbulent. Behind him, he sees the distinctive twin-boom silhouette of a P-38 following him down. This should be suicide for the American pilot. The Lightning is notoriously bad in sustained turns at low altitude. Its heavy weight and high wing loading make it sluggish. Shimada grins inside his oxygen mask. He'll reverse hard. The P-38 won't be able to follow, and he'll have a perfect deflection shot. But when Lindbergh's Lightning levels out at 500 feet, something is different. The American fighter accelerates. At sea level, where 0 fighters traditionally hold every advantage, the P-38 is matching their speed, exceeding it. Shimada's eyes widen. This isn't possible. The Mitsubishi A-6M0's maximum speed at sea level is approximately 282 miles per hour. The P-38J Lightning's maximum speed at sea level is 340 miles per hour, but that's at war emergency power, burning fuel at catastrophic rates. At cruise settings, especially at the end of a long-range mission, American fighters shouldn't have this kind of performance. Except Lindbergh isn't at cruise settings anymore. He's advancing throttles, manifold pressure climbing to 46 inches, war emergency power. Because of the fuel he's saved using his cruise technique, he has reserves for a fight that conventional P-38 operations would never allow. He closes the distance in seconds. Shimada tries the desperate brake turn anyway. His 0 responds beautifully, rolling knife edge and reversing, but Lindbergh doesn't follow. He makes a high-speed slashing pass, his .450 caliber machine guns and single 20mm cannon converging on the Sonya. The Japanese bomber staggers, smoke trailing from its engine. "I'm hit," Shimada radios to his escorts. 2 Zeros dive to assist, but they're facing the same impossible situation. The P-38s have fuel. They have speed. They have altitude advantage. Everything about this engagement favors the Americans when it should favor the Japanese. Second Lieutenant Merrill Smith, flying as Lindbergh's second wingman calls out, "3 bandits, 4 o'clock high." Lindbergh glances at his fuel gauge. Enough for 10 more minutes of combat. Last month he'd already be calculating the emergency glide ratio to the nearest carrier. Today he rolls into another attack. The dogfight lasts 8 minutes. When it ends, the sky over Seram Island contains wreckage, not aircraft. Shimada's Sonya has crashed into the jungle. 3 Zeros are shot down. The remaining 3 Japanese fighters flee toward Ambon, their pilots reporting to intelligence officers that the American P-38 seconds somehow had unlimited fuel and impossible performance. MacDonald reforms his squadron. All flights, fuel check. One by one the pilots report. Every P-38 has sufficient reserves for the return trip. Several have enough for an additional hour of combat. These are numbers that should not exist. The formation turns northeast toward home. They cruise at 1,600 revolution per minute, 30 inches manifold pressure, auto-lean mixture. The engines hum smoothly, temperatures nominal, fuel consumption optimal. Below them, 640 miles of hostile ocean that has claimed so many American pilots. Today, it claims none. When they land at Mokmerdrome 4 hours and 20 minutes after takeoff, the flight line crews count the returning aircraft. 20 P-38s took off, 20% return, 0 losses to fuel exhaustion, 0 emergency landings, 0 engines showing stress from the illegal operating procedures. The maintenance officers inspect Lindbergh's engines that evening. After 12 combat missions totaling 67 flight hours using his technique, the Allison V-1710 seconds show less wear than engines operated under standard procedures for the same duration. The spark plugs are cleaner. The cylinder compression is higher. The oil analysis shows lower metal content. Patterson, Allison's field representative, examines the data in stunned silence. "Gentlemen," he finally says, "I need to call Indianapolis." By August 15, 1944, Lindbergh's technique is officially incorporated into P-38 operations throughout the Pacific Theater. The formal designation is Extended Range Cruise Procedures, but every pilot calls it flying the Lindbergh way. The impact is immediate and measurable. The P-38's combat radius extends from 570 miles to 750 miles. Missions that were impossible become routine. Targets that were unreachable become vulnerable. Fuel exhaustion losses drop from 23 pilots per month to fewer than 3, and the kill ratios shift dramatically. American P-38 squadrons, now able to reach deep into Japanese-held territory with fuel reserves for combat, begin systematically destroying enemy air power. The 475th Fighter Group alone shoots down 197 Japanese aircraft between July and November 1944, compared to 94 in the previous 4-month period. Japanese pilots report to their commanders that American fighters have somehow developed new engines, that the P-38s they face in August fight with energy and aggressiveness impossible just weeks before. Intelligence officers struggle to explain how American aircraft are appearing over targets far beyond their supposed maximum range. They never suspect the answer is as simple as one man questioning what everyone else accepted as truth. The story of how one civilian rewrote aerial warfare is almost over, but the ending might surprise you. Make sure you're subscribed so you don't miss our next documentary about the hidden heroes of World War II. Hit that like button if you're enjoying this story. The war ends 15 months later. The final statistics tell a remarkable story. By September 1945, Lindbergh's technique has been adopted by every P-38 squadron in both the Pacific and European theaters. Over 8,000 P-38 pilots are trained in extended-range cruise procedures. The technique contributes to 1,430 additional enemy aircraft destroyed, targets reached only because of the extended combat radius. Fuel exhaustion losses dropped by 67% across the entire P-38 fleet. An estimated 234 American pilots survived the war who would have died in fuel-related accidents using conventional procedures. Allison Engine Company quietly revises their technical manuals in October 1944. The prohibited operating range becomes the recommended cruise setting. Page 47, paragraph 3 is rewritten. For maximum range efficiency, operate at 1,600 revolution per minute with manifold pressure, not exceeding 30 inches of mercury and auto-lean mixture. No acknowledgement that this directly contradicts their previous specifications. No mention of the civilian who proved them wrong. Robert Patterson, Allison's field representative who initially opposed the technique, writes a letter to Lindbergh after the war. "Sir, I owe you an apology. Your instincts about engine efficiency were correct, and our testing protocols were incomplete. The V-1710 is a better engine because you questioned our assumptions. Thank you." But here's the remarkable part. Lindbergh refuses credit. When aviation journalists try to interview him about his specific service, he declines. When the War Department wants to issue a commendation, he quietly suggests they honor Colonel MacDonald instead. When General Kenny writes his memoirs and wants to include a chapter about Lindbergh's miracle, the aviator politely requests his name be minimized. In 1954, President Eisenhower restores Lindbergh's military commission and promotes him to brigadier general in the Air Force Reserve. At the ceremony, reporters ask about his wartime contributions. Lindbergh's response is characteristically modest. "I simply applied some old lessons to a new problem." The real heroes are the pilots who trusted the technique and brought their aircraft home safely. One of those pilots, retired Lieutenant Colonel James Watkins, writes to Lindbergh in 1968, "Sir, I never met you personally, but I flew with the 475th from July 1944 until war's end. I want you to know that every time I landed with fuel to spare after a long mission, I thought about you. Because of you, I came home. Because of you, I met my wife, had my children, lived my life." How do you thank someone for that? Modern aviation still uses Lindbergh's principles. Current cruise procedures for reciprocating engines emphasize lower RPM with optimized manifold pressure and lean mixture settings, exactly what he demonstrated in 1944. Flight schools teach LOP operations, lean of peak, a direct descendant of Lindbergh's technique. The man who crossed the Atlantic solo in 1927 indirectly taught the world how to fly efficiently for the next century. Charles Lindbergh dies on August 26, 1974, at his home in Hawaii. His obituaries focus on his famous transatlantic flight. Few mention the Pacific. Almost none detail his engine technique that saved hundreds of lives. Perhaps that's how he would have wanted it. The lesson endures anyway. Sometimes the most radical innovation comes not from accepting what experts tell you is impossible, but from asking a simple question. What if they're wrong? The P-38 pilots who came home when they shouldn't have, they know the answer.